Good evening, alumni, students, faculty, and staff colleagues, and friends of UNC Asheville. Thank you all for joining us today. As Dean of the Natural Sciences and on behalf of our UNC Asheville community, I welcome each of you to our 2022 Parsons Lecture. Now, before I continue, take out your cell phones. Everybody grab the cell phones. Put them on vibrate or silence. Okay. That always happens in church, that somebody's cell phone will go off in the middle of the sermon. So, since 1998, and thanks to the generous funding from our alumni, our mathematics department has honored our institution's first chair of mathematics, Dr. Joe Parsons, by hosting this annual lecture series. So this lecture series aims to engage in a general audience in relevant mathematic topics that maybe you did not know were actually relevant. So let me first of all give some mad props to our mathematics department. Our mathematics colleagues deliver a top-notch, state-of-the-art mathematics curriculum with concentrations in statistics, theoretical mathematics, applied mathematics, teacher licensure in mathematics, and they also have minors in mathematics. Our colleagues and our students promote mathematical literacy through the Asheville Initiative for Mathematics, through the Science Olympiad for grades K through 12, also through the Association for Women in Math and the Mathematical Association of America, through the Marvelous Mathematics Club, and through our campus math lab. I admit I am eagerly awaiting my invitation to the Math Talent Show. Before COVID, that was held annually, and it was always a treat. So, please let us first give our acknowledgement by clapping, and I'm asking Becky Sam, the chair of our department, the current chair of our mathematics department, and all of our faculty and staff colleagues in the mathematics department, will you please rise for us all to go? Don't be shy, please stand. Oh, hey, okay. Okay, let's also now ask our current students who are majoring in mathematics or statistics or some of the concentrations, please stand and be recognized. Yay, current math students. So will our alumni, UNC alumni who majored in mathematics, please stand as you are able, or raise your hand and let us recognize you. Now, put someone on the spot, or a couple of someone's on the spot. If you were students of Dr. Joe Parsons, will you please stand and raise your hand so we can acknowledge you? Any students? Well, yes, well, we can try. They're here in spirit. So, thank you all. Let us now welcome Dr. David Pfeiffer to introduce our speaker.
Yeah, thank you very much for coming. I'm so thrilled to see you folks here. Yeah, I'm honored. I want to just say a little bit about Joe Parsons. He was the sole member of the math department for a while. He was also a dean of the school. He was the one who decided, he worked to design this campus and putting the library facing Pisgah. You know, when you're on the steps and you see Pisgah, that was Joe's idea. He worked on the first humanities program. He was a wonderful faculty member. And I should mention too that the money for this talk was actually donated by one of Joe's students who wanted to honor him. So I wanted my students to hear that. So, just in case, you know. Okay, so I'm very honored to be here introducing the speaker today. So yes, I'm introducing Professor Autumn Kent. She grew up in Goldsboro, Our Goldsburg, North Carolina, so nearby, went to UNCA. While she attended UNCA, she got a major in mathematics and literature. She took several courses from me, and in fact did undergraduate research with me. I could tell one story, I won't tell a lot, but one little story that, you know where the fountain is over there under the breezeway in the math department? That big piece of sidewalk, we would do math on that sidewalk, and I do remember a day that she showed me, we were working on 3 manifolds, which are these things that sit in 4 space. They're 3-dimensional, but they have to sit in 4 space to really see them. And she explained to me how you could glue together 2 tetrahedra, and the boundary of this would be a figure 8 knot. And we did that. It took us about 2 hours with we went through a big box of sidewalk chalk, and it was great. It stayed on it didn't rain for a little while. It stayed on the sidewalk, and people commented for weeks about that. So she graduated from UNCA, double major in math and literature. She went on to graduate school at the University of Texas at Austin, working with Cameron Gordon, a great topologist. She's received several grants and awards. I just want to mention a couple here. An NSF Career Award from 2014 to 2019, a von Neumann Fellowship at the Institute of Advanced Studies, spent a year at the Institute of Advanced Studies. That was 2015-16. A Simmons Fellowship. She was a professor at Brown University from 2006 to 2010. In 2010, she moved to the University of Wisconsin at Madison and is now a professor and the director of graduate studies in the Department of Mathematics. I also wanted to mention that she's been a vocal advocate for women and marginalized people in mathematics and the STEM sciences. And I am incredibly proud and thrilled to have Autumn Kent giving our lecture today. So, Autumn, thank you.
Is it on? You can hear me? Okay. Thank you, Dave, for the lovely introduction. Yeah, so Dave, had a big influence on me when I was here. There were 3 professors that really influenced me a lot. There was Sherry Gale, who was the math department chair at the time, and Elizabeth Allman, who was here for a little bit, and Dave. And I think, Dave was probably the reason I got into the grad schools that I got into with his letter of recommendation, and I learned a lot from him, and he was really I don't think he understands how instrumental he was in me. I probably wouldn't have known about graduate school if it weren't for Dave, but just spreading his love of math and his energetic spirit. And so thanks so much, Dave. It's they've got it taped off here where I can go. Yeah, so it's kind of surreal to be back, and I sat in one of many of these chairs for humanities lectures when I was taking the humanities sequence here. And I don't know if I have too much more to say about that, but I want to talk to you about video games, okay? So some people like video games. I like video games. And there used to be a video game called Asteroids, and you could play it on your Atari 2600. And you would plug that into your television. And to show you what I mean, because some of the people in this room probably don't remember Asteroids. My calculus students don't know what Cubert is, which made me really sad. So let's see. So this is Asteroids. Oh, I died. Okay. So this isn't the original. Asteroids. This is just kind of a clone in JavaScript. And if you, okay. Be careful. You could just kind of get mesmerized. It's like a lava lamp. They don't hurt each other. But you'll notice this guy on the right, it's not perfect animation either. He comes back on the left. So on your TV, you know, on the right side of the TV, you come back around on the other side if you watch the asteroids. And if you watch this one coming down in the bottom, will show up in that corner, and then over there, and then come down, okay? And you play this on your TV, and if you go to my webpage, this works, you know? And so if I fly, you know, and you shoot the asteroids, it doesn't have any sound or scoring, but you can get rid of the asteroids. Oops, I'm not even very good. But notice that I went out the left side of the TV, and came out the right. And if you go at the top, yeah, whoops. Well, if you don't hit an asteroid, there you go. I come out the bottom. And then I've set the lasers so that in the original game, in the original game, the lasers sort of died out very quickly, but I've set them so that they go pretty far. So I can just kind of clear the asteroids like this. And so, yeah, so that took care of those guys. Take that, okay? And then, you know, you can go to my Google my name and go to my webpage. You can play yourself, okay? But you can't play on your phone, so that'll keep you from getting distracted. But there's no cap on how fast I can go in the ship. The bullets have kind of a fixed velocity, but I can just go forever. It kind of gets mesmerizing. But notice I kind of go everywhere. You know, it'll make you nauseous too, so you can watch out. But like if I go in this direction, this is like the whole talk. Just gonna do this. But you notice you kind of go everywhere. That'll be important later. And then the bullets kind of die out, which is nice because now we can see the ship. Yeah, okay, so that's asteroids. You could play it on a different size TV. You have a really wide TV. See that? This is harder to put this down. Whoop. You can kind of do a little wall of bullets. Whoop. And then they go away though. Let me clear this one and show you. Now what I want to do today is kind of imagine that we're the ship captain. So this is like, I don't condone smoking, this is like the cigarette asteroids. So it's very skinny. Now notice you see yourself right away. This would be disconcerting, looking at your own butt. And it would be kind of horrible place to live, right? I mean, if you want some kind of free time, some space. Dave took me on a hike this morning. But you know, if you want to go on a little hike or stretch your legs, you kind of have to go this way. And then there's this one really short direction. Okay, so that's kind of a crowded place to play asteroids. You could also play on a parallelogram. They don't make TVs like this much. It's the same game. Sorry, I'm rustling the microphone. And notice that if I could still identify the left and right of the parallelogram, just like before, because it's just each side of this parallelogram is just a copy of its sort of twin on the other side. And let me clear some of these out. The asteroids are fun for the discussion, but not so much when you're playing, or for playing, but not for the discussion. But see, I go out the bottom, clear them while I go. And if I go in the side, I come out the same point on the other side. And now this one, I should probably clear some of these. Okay, this one's kind of more mesmerizing. So you're really jumping around a lot. You know, part of this is like the frame rate, just kind of sampling the ship whenever we take a look at it. But there's kind of a behavior we're noticing that if you kind of point yourself in any direction, you can kind of go anywhere. This would be a cool universe to live in, maybe, because if you got lost, you could just head off in a random direction and you always come home. Okay. So that's like asteroids on a parallelogram. And then I'm not going to talk about this today, but you can also play on more interesting TVs. So this is what's called an L-shaped TV. And, whoops. So this is weirder. So if I go in here, I'll come out there. But if I come over here, whoops, I die. But if I come over here in the bottom, I come out the top. And then if I come out this side, I come out over here. And then over here, whoops. Of course, I come out, over here. And so like parallel sides get identified, okay? And that's kind of weird because the right side of the TV is actually broken up into two pieces, and one of them's identified to this bottom part of the L, and the other is to the top part of the L. These are all kind of neat places to live, I guess, and they're flat, just like a piece of paper. And so you could do geometry in this space. You could draw triangles and talk about straight lines and angles. But it turns out that this particular universe really doesn't want to be flat at all. And so let me just take a second to show you something weird. So there's this one point that's kind of not flat. So something weird is happening at the corners. So imagine if you were right here. Hold on. Let me do my trick. There's a theorem called the Poincare recurrence theorem. It tells me I can do that. Okay, so I start here, and what I'm going to do is I'm going to walk around this point in a circle. Uh-oh. No! Okay, well, at least it got rid of the bullets, too. Okay, I meant to do that. Okay, so I go up here, and I'm going to turn left, and I'm going to go out, and now I'm going to walk around that point. So I've turned left twice now. I turned left twice. And now I'm going to turn left again, so that's 3 times. I'm going to turn left here, and that's 4 times. I'm going to turn left 5 times. And now I've turned left 6 times. Seems unusual. 7 times. 8 times. Not done yet. 9 times. 10 times. Whoops, I screwed up. I was too far to the right. What was that, 10? Then 11 and 12. So it took me 12 left turns to walk around that one point. So if I want to walk in a square around a point, I can take 1 left turn, and then 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 I come back. So that's there's 360 degrees, and every time I take a left turn, I'm turning 90 degrees. So instead of there being 4 turns around, there's 12, okay? So instead of there being 2 pi angle around that point, there's 6 pi or something. So anyway, this is a very weird TV, okay? But we're not going to talk about that. So let's go back to my title slide. I don't know when we started. Do you know? Okay, so let's talk about this. Sorry, I'll make sure I can control it. Okay, here is our television, and we're playing asteroids on it. Okay. And we notice that if you go out the top and you come back in the bottom, and you go out the right, you come back out on the left. So you come out the top, you enter the top, and you come out of the bottom. That's like you're on a cylinder. Okay? So if you didn't do anything when you hit the left and right, you would be playing asteroids on this cylinder. Okay? And then actually we glue the left and the right, though, so we're actually playing this on a donut. Okay? Because you glue the ends of that cylinder together, so the left and the right side of the TV are now these circles, and they get identified. Whoops. Right. So in math, we'd call that a torus, but we can just call it a donut. Okay? Okay. Okay, I want to think about this place. So I'm going to straighten us out a little, and we're going to think about our ship captain. And she's living in this universe in this little ship, and her job is to shoot these asteroids. Hold on. Well, when we did the cigarette version, we noticed that you could see yourself real soon, right in front of you. This is not a nice place to live. Okay? So actually, if you think about how light behaves, my arrowhead got cut off on the top there, but the light coming at you would be, coming from behind you. So you could look ahead and you'll see yourself from behind. Okay? A lot of us have probably experienced this, like at the salon or the barbershop. Okay? So here's a very 1985 version of me at the salon, and let's say my backside is green. So when you look at the reflection, that's the other side of me. And then imagine that I'm standing in front of this green bordered mirror, and then there's a big mirror behind me also. And so when you look in the mirror, I see my reflection, but then in the mirror behind me is a reflection of my back, and then I'll see that again in the mirror in front of me, because the mirror in front of me can see the mirror in the back of me, okay? And so on, okay? And so you'd see this picture, and there's lots of beautiful pictures of this online, or if you've ever been in an elevator that has mirrors all around, you see yourself forever, and it just sort of continues forever. Okay? So living in this universe would kind of be like this, except you wouldn't see this green version. You would just see the back of you over and over again. Okay? So this is also like a trope in horror movies, right? Where you like look into the next room, and it's the room you're in, and it's some terrifying thing, You go and run, and it's you, and it's startling. Okay, so that's what it's like to live in this world. Okay, but it's kind of worse than that. If you imagine living here. Okay, because not only would you see yourself straight ahead, if I look to the right, I'll see myself. She'll see herself. And then if she looks over there, she'll see herself. And then if she looks, way up there, she'll see herself. So she's going to see a copy of herself. Like this is like the elevator when all the walls are mirrors. You can look in some weird direction and you'll see some copy of you, like really far away. Okay? So this universe, even though it seems kind of claustrophobic, like it's very small, the TV is very small. If you lived there, it's like that elevator. It seems really big, okay? And so in almost every direction you look, you're going to see a copy of yourself, okay? And so this is maybe not such a fun place to live, especially, if you're all alone. And you spend your life here seeing a copy of yourself and all these other copies, all around you. I know some people who would like that, but, it's not, it's kind of a frightening place to live, okay? It would feel very open, but you would see yourself everywhere, okay? I wouldn't like it, okay. Okay, but let's go back to this. Let me get some water. And I'm a professor, so you can yell at me or shout out questions. Okay, so this is the TV of my childhood. It's called a 4:3 TV. Okay, so that's the aspect ratio. So if it were, 40 inches wide, it would be 30 inches tall. Okay. We don't actually measure TVs using, we call the aspect ratio, and then you use the diagonal to mean how big the TV is. And actually, while we're here, let's sort of make another assumption about our ship captain. So when I was a kid, I had a 9-inch television, okay? So it's like this big. I watched like Cape Fear on it. It was like a line, okay. So this ship captain is used to being played in the game of asteroids. So you play her on a bigger TV, she's used to that, okay? Like maybe her universe seems bigger and roomier, from time to time. Maybe the image of herself that she sees gets a little smaller, but the shape of the TV is this 4:3 TV all the time, okay? So when we're talking about the aspect ratio, that's like what we're thinking of, okay? And this is kind of like the old-fashioned TV. You don't find these much. I don't know if they even sell these anymore. Okay. So your TV now probably looks more like this, and that's a 16:9 TV. Okay. And yeah, and so what I want to do is I want us to act like we're some outside force, okay, or deity or something. And I want to ask the question, like, what would happen if she got teleported into this other TV? Okay? So my question here is, would she notice? Right? She's used to things, maybe the size of the TV changing, but the shape, it seems like we've changed the TV in some fundamental way that's different than just changing the size, because like the ratio of the two sides is different. Okay? It's a different shape TV. And we know this because, it's a different experience watching this TV. When 16:9 TVs came out, television channels would just stretch the old show, and everyone looked like a linebacker, because they're stretched really wide. And you'd be like, man, that's not my show. If you scale it up, put it on the Jumbotron, as long as you preserve that aspect ratio, it looks good. Okay. Sometimes when giving these talks, this happens, and this is bad for it to happen during this talk, because these are important. That's what you're talking about. So that's my question. Would she be able to tell? Okay. These are like two different universes we could put our ship captain in. Okay. Okay. So let's think about this. Okay. So here she is, and I just want to draw kind of a little bit of her field of view so we can sort of think about this. And we think about, when you look forward, you sort of have a field of view, like that. And then you have some field of view if you turned your head and looked out the right side of the ship, okay? And notice that she's probably used to her world being asymmetric, When I was a kid, I thought a TV was a square, okay? But it's not a square. It's slightly off. So when she looks to the right, the copy, she could even turn, and look at herself head on like the other way. She would look a little bit smaller when she looks to the right. Okay, she's a little further away. Okay, and so perspective, two-dimensional perspective, would make her appear smaller in that direction. So she'd be used to that. And maybe there's nothing to do except shoot asteroids, and they're gone pretty quickly. So maybe she just spends a lot of time thinking about where she lives. And so she could, after the teleportation, something feels wrong. Okay. And now when she looks in this direction up, she looks normal. It looks like they haven't even scaled the TV or anything. But then when she looks to the right, she looks a little bit smaller. It's actually, the ratios are so close, it's almost hard to tell that you would look smaller, but you're a little bit further away. Okay? So she knows it's still asymmetric. It's not symmetric anymore, but it seems a little stretched further in that one direction. Okay? So one weird thing about living in a universe like this is you can throw yourself a rope. So you throw yourself a rope, you try to play tug of war with yourself, but it doesn't work. So you just pull yourself backwards. Okay? But she could throw the rope to herself and hold on to it like this, and like measure it and say it's 3 meters or something, whatever unit you like. Okay? Okay? And then let's say that after the teleportation, she does the same thing. Okay? And it's also 3 meters. Okay? So it doesn't seem like it's just been scaled. And then like in her old universe, when she looked east and did the measurement with the rope, she'd get, say, 4 meters. So that's the 4-3 TV. Okay, so if she did that down here, she would get 16/3. Okay? It's a 16:9 TV. So if you scaled the TV so that the left side were 9 meters, then the bottom would be 16 meters. Okay? So, something's wrong. Okay? I don't want to get too mathy here, but 16/3 is bigger than 4. This is what we expected. Okay? That's about the limits of your computations we need to do today. Okay? So, she might start to suspect something, that maybe okay. So she's starting to suspect something, that maybe she's not in Kansas anymore. Okay? Kansas is pretty flat, like this too. Okay? But she's pretty smart, and she knows that, in Star Trek or something, when they teleport you down to the planet, they have to tell the transporter where you're going, but they don't just, let the direction they're facing be random, okay? So you have to tell the transporter, like, which way you're facing when you're standing on the planet, okay? And sometimes they use that to their advantage. They want to sneak up, use the phaser or something, okay? So she knows that maybe she's just looking in the wrong direction, okay? So maybe the ratio is wrong for that north-south, east-west orientation. But maybe she just landed somewhere else in her universe. So what if we teleported her like this? Okay? And so maybe we even, teleported her, turned her some direction, and then scaled the TV. And so maybe what we're doing is maybe that aspect ratio with those 2 directions, you have a 4 and a 3, maybe what happened is we just turned the TV in some funky way and scaled it maybe and made it a bigger TV. And then, we just had to be looking in this direction instead, and then everything would look normal, at least how we expect it to if we were in a slightly bigger TV. So you imagine this doing something like that. Okay? So it's not obvious that that didn't happen. Okay. Okay. Okay, let's go back. 4-3 TV. Okay. The 16:9 TV and the 4-3 TV, this can't actually happen. There's no way. They're really different TVs. Okay? And we'll talk a little bit later about what I mean when I say they're really different. But they're really different. She would never be able to find that same ratio anywhere in that 16:9 TV. Okay? But so you might say, oh, well, just all TVs give you different experiences. End of lecture. Okay? But let me just show you an example where you do get the same universe, where she could never tell. Okay? And it's not hard to see. So let's go back to a parallelogram TV, but this is much more extreme than the parallelogram I showed you when I was actually playing the game. So notice that it's important here that the top left corner of the parallelogram is directly above the bottom on the right side, okay? And then it's just a parallelogram, okay? So this is like wacky TV, okay? It's not It's not, you don't just have a nice ratio to explain it, okay? It's just this parallelogram, okay? We'll see later how we describe this, okay? So let's teleport her out of 4:3 TV, the TV of my childhood, into this wacky TV. Okay, and I just, we just pick her up and put her down. We don't change how big she was or anything. And then let's put in a little bit of her perspective here. And what I want you to notice is that inside of this thing, there's a rectangle that's exactly the same shape as her original TV. And so actually these vertical lines make loops, and I could actually cut my wacky TV into these two triangles. And then I could, just identify that with the original TV. So they're actually the same TV. Okay? It's not a wacky TV. It's a different TV, but it's the same universe that she would never be able to tell. Okay? So somehow the issue was we just took our 4:3 TV and we sort of cut it up into pieces and rearranged the pieces and just remembered how we glue everything together. Is that okay? Okay. So I said that the 4:3 TV and the 16:9 TV, they're different, okay? And we'll see a little later what I mean when I say they're literally different, Yeah, so there's some way to distinguish them. The 16:9 TV is a little skinnier, makes a skinnier donut. It's like the donut you buy at the fair or something, and this is like a Krispy Kreme, or the one you make at home, We just make donut balls at home because it's easier. And so we have these two TVs, and now I want to ask, maybe we can communicate between these two universes, okay? Like in Rick and Morty, you could have a gun that does this and sends you to the other universe, okay? And so maybe how do we, is there a way for us to travel from one to the other, okay? Could we travel through a family of universes to get from one to the other? Is there some natural path in the multiverse to get me from one space to the other one? Okay. So sorry, there's a shadow on the screen. That's not important. It's like Mystery Science Theater or something. Okay. So I want to talk about how do you make this a mathematical thing. What am I talking? I'm just giving some silly talk about this multiverse and moving around between these different donuts. Okay. So what I'm going to do is I have this green area here at the top, and that's it's the plane. I'm just drawing the plane, but I don't care about anything below that green line. Okay. I'm just interested in the upper half plane, okay, that's above that line. And I'll think of the bottom, that's the number line. I have little kids, so that's what they call that. That's cool. And so I have 0 there, and I'll just put 1 there, okay? And now if you give me any point up there in that plane, that's not on the number line itself, then I get a parallelogram, right? And I'm just assuming that the base of my parallelogram is just that line segment from 0 to 1. And if I'm interested in just the shapes, that's fine. I can just scale my TV until the bottom of the TV has length 1. Okay, so any point up there gives me a parallelogram. Okay. So 1 way over there, down there, okay? They start to look kind of skinny, right, when the point is really close to the line. Okay. We could even, now, this is some space, it's this upper half plane. It's a space of points, okay? And we pick any point in this upper half plane, and we get a parallelogram. So we would get a universe to play asteroids on, okay? Because we could make our TV like that and play asteroids on it, okay? And then we could consider like a path of points in this upper half plane, okay? And then that would give us some path of parallelograms, which is maybe not something like the general public does, like think about a path of shapes. But when you see it all the time in movies, like, you see like, some shape, being cascaded across the screen, or, if the protagonist is hallucinating, there's like shapes, moving around. And so, how do I go from this parallelogram to the parallelogram at the bottom? I would just move and I'd have this path of parallelograms, okay? Do y'all want to see it again? Okay. I'm proud of this. There it is. Okay, do it a couple more times. Whoops. There we go. Okay, so that's what a path of parallelograms looks like. So that's like a path of universes, okay, that you're playing asteroids in, okay? So it's like a path in some, space of different universes. But these moving, I'm going to do it one more time, not to brag, but just to show you one more time. But that kind of always makes me think of Venetian blinds for some reason. I don't know if young people have probably never installed Venetian blinds, but you have a window and you have maybe a rod, and you twist the rod and it blocks the light or lets the light in. Those are blinds, okay? And you can think about some Venetian blinds. They look like this. Oh, sorry. Okay, so there's some Venetian blinds, okay? And I've stretched them out to hang them, okay? So put them back. And now if I've got the Venetian blinds over here, and say I want to install them on that window over there, I want to move the Venetian blinds, okay? Now if my buddy is up on a ladder and he's going to hang them, I could just pick up the whole set and take it over there like a rational person, okay? Or I could just grab the top of them and move them over there and give them the top of the blinds, okay? Now, so we're faced with the question of like, how should we move the top of the Venetian blinds from over here, say to over here, okay? Now, if you have little kids, the little kid would do this, okay, and ruin the blinds. They get all tangled up, and you just drag the blinds across the floor, and it's really an extreme thing to do to them. It's not good for the blinds. Don't do that. Or would I care? I'm not, unless I'm paying for them. Okay. Another thing you could do is lift the Venetian blinds and then just walk over like this and then drop them. Okay. You could do that. But you probably wouldn't do that if you had to put them down, right? If you wanted to hang them, hand them to the guy, then sure. But if you wanted to put them down, that's what you do, maybe. But you might not hold it up high the whole time. Okay. So now I think what I would do is I would take the top of the Venetian blinds and I would just kind of pick them up and go like that. Okay. So I probably wouldn't follow a perfect circle like this, but there's like a circle and I could move the Venetian blinds like that. Okay. So that's like moving the top of the blinds along that circle. I can show you that one again too, because that one's fun too. Okay. And it turns out that that's the least stressful way to move the top of the Venetian blinds over to the different position on the floor, is to pick the circle starting where you wanted, and then it's a half circle, and then you go over here, and then you land at this point. And so what do I mean when I say stressful? Well, if I just yank them along the floor, it's just shearing like all in one direction. And that's really extreme. But the kind of stress that I'm worried about is if you take a rubber band and you pull it really tight, then the rubber band stretches this way, but vertically it'll contract some. Okay. Another instance of this is imagine putting on your jeans and then giving the waist a full twist around your body before buttoning them, right? that would hurt a lot, right? You wouldn't want to do that. So that's putting a lot of stress in kind of like it's squishing everything in one direction, and then, it's not stretching in the other direction in that situation. But it's like the rubber band, okay? You're sort of stretching in one way and compressing in the other way. And so that's called quasi-conformal distortion, okay? And there's a mathematical way to make this precise of like stretching in one direction and, not, and squishing in the other direction and stuff like that. And, you can do this and you use what's called complex analysis. Oh, okay. Okay, anyway, I guess we're not allowed to talk about that. Okay. So here's our circle from the Venetian blinds. Okay. It's pretty. It's a half circle. Okay. It forms a right angle with this line, this half circle. Okay. Okay. And then there's something else that meets that line at a right angle, and it's just a vertical line. Okay. And then I'm going to draw a few more of these. Because this is like our space of games of asteroids, our space of universes, right? It's this upper half plane. Okay? And these are the efficient paths. It turns out that just lifting the Venetian blinds and then lowering them again is very efficient and minimizes this kind of stress. So just pulling them straight up is also kind of an efficient path. And what do we call an efficient path? We think of it as a straight line. Okay? So these are kind of our straight lines in this universe. Okay? We could put in some more and make a triangle of them if you wanted. Okay? And so this is a very evocative picture. And I claim that you can start doing geometry in this plane where these are the lines. Okay? So this is actually, it turns out by a miracle of nature, that this is what's called the hyperbolic plane. Okay. It's not going to mess with that. Okay. So that's the hyperbolic plane. And it came up, in geometry, it was always a problem that in geometry, if you have a straight line, like in high school geometry, you have a straight line, and then you pick a point that's not on the line, then there's a unique parallel line through that point. Okay. So it's hard to derive that fact from the axioms of geometry, like in Euclid, and it's hard because it's impossible. Okay, you can't actually do it, and so this hyperbolic plane is a beautiful example of such a thing. And so these green half circles and vertical lines, those are straight lines. There's some way to put distance on this thing so that those are straight lines, and it turns out by a miracle it's the same as this efficiency of stretching of parallelograms, which is incredible. I'm still not over that years later, and. Right, and if you pick, the top of that funky-looking circular triangle, that's a line, and then you pick a point over here, on this line, and that's a line that doesn't intersect that line at all. And then there's actually infinitely many lines, through that point that'll go through there. So this is a beautiful geometric object, and it's the foundation of something called hyperbolic geometry that comes up a little bit in physics and relativity. But we don't need to know anything about the geometry. It's just sort of a beautiful coincidence that this universe we have and the efficiency of stretching. You think it, I want to say that this efficiency of stretching, you should think about it if you're watching a movie on TV, it's kind of measuring how distorted the image looks. If you apply this stretching. Like if you watch a movie projected on a rubber band and then you stretch it, it's going to look weird, right? So there's some number that measures that. Okay, so let me go back to these numbers. Okay, so here on the bottom we have the number line again. And then there's a beautiful idea that let's throw in another number called I, okay, which you may have heard of. And it's the square root of -1. Okay? So we'll just make up a new number, and we'll call it I. Okay? And what we'll do is we'll put it in the plane right there, on that vertical line through 0. Okay? And then what we can do is, like, if we pick any point in this plane, we can think of it as, the Descartes, decided, like, oh, this is great. We can think about the plane as, like, just given by two numbers, how high you are and how east and west you are. Or if you play Minecraft, you have the first and last number, So I'm trying to keep it relevant for the kids, So you have these numbers that tell you your position. And so actually you can write every point in here as a complex, what's called a complex number, and it's some number x, a regular real number, plus some other real number times this number I. Okay? And if you play with this, you can just formally just play with these things, and you can multiply I by itself, you get -1, so you can multiply these things, and you get new complex numbers. Okay? So it's kind of like real numbers, but it's a whole plane. Okay? And actually, there's complex numbers below this line, but I don't care about those for the talk. Okay? Okay? So now we can think of every universe for asteroids as a complex number. Okay? It seems like I'm changing gears a lot, right? You want to like think of it one way, and then we got rid of the parallelograms completely, and now we're just thinking of the universe as this point, this complex number. Okay. Right, so now anytime we have a parallelogram, we have an associated complex number. That symbol is omega, Greek letter. Okay? And so anytime we have a parallelogram, we have this number. Okay. So this is the TV I thought I had when I was a kid, the square TV. Okay? And it corresponds to the complex number I. Okay? And it's a square. And by the argument we gave before about cutting along the diagonal, this is actually the same as this parallelogram at the level of the universes, right? If we teleported her out of the square and into this parallelogram, she'd never notice. Okay? So our description of these universes as numbers is redundant. Okay? So the same universe is up there lots of times. Okay? So actually, if you think about the complex arithmetic a little, once you get used to this sort of thing, all we've done is added 1 and moved that point by 1 in that direction. So moving horizontally is like adding a real number. And then by the same argument, by the same logic, you can do that in this parallelogram too. You could cut along a diagonal, right? And that would make an even, this is a wacky TV, sorry. You could do it again and get this really sort of sheared TV, but she wouldn't notice. Okay? It's just the TV that's weird. Okay? It's just how we're thinking about it from out here. And then 3 plus I is the same too, and that's really skinny. And so actually, any whole number plus I will give you the same universe. Okay? So it's super duper redundant. Okay? So this is kind of like a multiverse, but it was repetitive, right? It's not the best description because it's like, the universes get mentioned a lot. Okay, so it's not really a good picture of what this multiverse should be. Let me show you another thing. So here's the universe for 2I. Okay? This is a very tall TV. They have these at the doctor sometimes. And they have a list of appointments or something. Or this doctor's on time and so on. And it's really just a TV they turn on the side or something. But that's relevant, actually, because if I turn that TV on its side and then scale it so that the bottom, which is the vertical side to begin with, so if I turn it so that the side is now the bottom, and then I scale it so that the bottom has length 1, I'll get a different TV. But you would never notice if I moved you from one of those to the other, because all I did was rotate it and scale, and I'm used to that. Right? I don't notice the rotation because I'm inside, So if you do that, what you get is, half I. And that makes sense. If you rotate it, the bottom has length 2. And so to scale it so that it has length 1, you have to multiply by half. Okay? And so the height, is coming down. Okay? So those are two of the same universes. Okay? Okay, so what do we know so far? We have this description of our Atari universes, or asteroids universes. And it's redundant, so we don't like that. So we know that if you have a universe, which I'm just thinking of as this number omega, then it's equivalent, it's the same universe as omega plus 1. Okay? And that's actually true no matter where omega was. Kind of, you have to maybe think about that a little. And then similar to this thing that we just had, that 2i and I over 2 are equivalent, a similar thing shows you this. That actually for any complex number, if you divide by that complex number instead and multiply by -1, you get the same thing. Okay. So it just so happens that, -1 over I is I again, which is kind of weird. Okay. And that's something you're not used to until you've played with these things for a while. So that's why I showed you this 2i and half I. That's the simple example we can all visualize. It's good to think about the other cases. You play with the complex numbers. Okay, so let me draw some lines. So there's some straight lines. Okay. And here's a region. So this is like a triangle in this space. Okay, so this green triangle. And what happens if I apply omega plus 1? It just moves to the right. Everything in it moves to the right by 1. Okay? And now, what happens when I do -1 over the number I started with? Well, that's harder to visualize, and I don't expect you to, but this is what happens. Kind of bizarre. But you should think of the triangle was up here, and then when you do this -1 over the number, what happens is the triangle kind of rotates in the hyperbolic plane, so it rotates around and is upside down. Sorry. So this, let me just show you again. So we started up here, and then we rotate down like this. Okay. And then we, so we could move, something to the right by adding 1, move that triangle to the right by adding 1, and then we could apply that other kind of move and multiply by -1 and divide by the number. And we can move this triangle around using those two moves. And you get everything. So actually, every single universe that's possible, you can get by starting with something in that green triangle and then, adding integers and then dividing and multiplying by -1 and continuing those. Okay, so actually, everything in that triangle, the triangle up there is actually encodes all the possible universes. Okay, so it's much simpler in a way than this whole plane. Now, let me just go back a little. This triangle. So if I'm on the left side of that green triangle and I add 1, I end up on the right side. Okay. So actually this, even on the triangle, the description's a little redundant. Everything on the left side is the same universe as something on the right side. So we may as well do what we did at the beginning when we were thinking about asteroids on a TV, right? You have this triangle, and everything on the left side is the same as everything on the right side. So let's just glue them together and make a cylinder. Okay? And now that cylinder will have a spike on the bottom, because there's this weird corner, at the bottom. And so we need to think maybe about what happens when you rotate. Okay? So what I want you to maybe think of is think of your hand as being the bottom of the triangle, and then like, you know, the bridge of my knuckles being the midpoint. And then when I rotate, sort of one side gets glued to the other side. Okay? So it's like take a line segment and rotate it through its center. And so one side of the line segment goes to the other side. Okay? So on the bottom of this tube that you've made, the gluing is kind of funny. So what you do is you make this cylinder, it's got this weird corner, and then I just kind of sew the bottom up like I'm making a pillow. You probably never made a pillow either. Okay. So you zip it up. Okay. And so that thing will kind of look like this. Okay. And it'll be a tube, it'll be infinitely tall. Okay. And it has these two corners on it. So remember at the beginning we had L-shaped universe? And there was like way too much angle around that one point. So these points, it's like there's not enough angle. Okay, so it's like a cone. Okay, so at the beginning it was like a cone, but it like had too much angle, which is something we don't. Think of like a parking structure, spiral staircase. But here it's just like a regular cone. I'm losing my microphone. So we have some cone points right there, okay? And like this point on the left is where I was, that's the square universe, at this point, cone point. And the angle there is pi, I think. Okay. And then at the other point is the obvious number, 1 plus I root 3 over 2, which is called a sixth root of unity. So if you want some homework, take that number and multiply it times itself 6 times, and you'll get 1. Okay, it's beautiful. Complex analysis is beautiful. And the angle there is 3 pi over 2, I think. So it's a little sharper. Okay, and this is, at the end, every single point in here represents a unique universe to play asteroids in. Where by universe we mean, you know, the universe up to scale, you know, where we could never tell if we were transported from one to the other. And so in mathematics, we call this the moduli space of flat tori. Whoops. Well, what would you call it? Thank you.
Thank you. Yeah, let me say that if you have any questions, we have a microphone set up. So if anybody wants to ask some questions, could you get up and go to the microphone? That's our technician. Does she have a question? Any questions for our speaker? We got somebody coming for the.
Sure. Okay.
Here we go. We got one person.
Oh, here we
Think
go.
about it.
Yeah.
Think about it. Yeah, we got.
Take
one
your
person.
time. Yeah.
Would that work if you cut television into more than 2 pieces for
Yes.
the different shape?
Yes. So there's actually a beautiful example that I'd love to do in. So the original game at the beginning is I just did in JavaScript, there's a famous example where imagine 2 squares, like 2 TVs, and then like draw a line segment on one, and then draw the line segment have the same length on the other one. And so then when you fly into that line segment from one side, you'll come out from the line segment on the other side, like in Portal, like the video game, but a 2-dimensional version. And so you have this portal that's like a line segment in each TV, and you're jumping back and forth between the TVs. And if you pick the angles of the line segments to be interesting, then actually the behavior as you fly around in the space is really weird. Could be really weird. So, at the beginning we noticed that if you fly on a regular asteroids game, if you fly kind of in a random direction, you kind of go everywhere. And so what happens in some of these double asteroids, with the line segments, you don't, so like on the donut, you go everywhere and you visit everywhere sort of equally frequently. So you sort of uniformly travel through everywhere. But like in this double TV, you can kind of like spend more time on one TV in some directions than you do in the other one. So it's really strange behavior. So yes, you can do that. And you can actually take any kind of polygon where the sides come in kind of opposite pairs that are just translates of each other. So notice like an octagon, you can take a stop sign and like the left side of the stop sign, you can just translate to the right side, and the top to the bottom, and this side to this side. And so any polygon like that, it doesn't even have to be convex. It could spell out your name digitally, Then you could make asteroids in that thing, and that's called a translation surface. And that's sort of closer to what I actually study. But that's a great question. Hopefully I answered. Yeah.
Hi, thank you. So I'm not used to thinking in hyperbolic space, but you made a comment that I thought think about triangles and kind of defining the whole set of universes or something like that.
Yeah.
That's like tessellation. Am I right?
That's right. Those triangles tessellated the plane.
So
yeah.
if we were to think of maybe, I'll use a technical term, another just different arbitrary nice space, would that be something common? Like in general, would a triangle be able to tessellate that nice space?
That's a great question. So the thing is, so if you look at that L-shaped asteroids, if you think about that hard enough, what happens is you realize that it's not actually on a donut anymore, and it's actually on a donut that has two holes. So imagine two donuts that have been welded together, with icing or something. Okay? And so you can talk about the same kind of thing, like the space of universes that are shaped like that two-hole donut. And it turns out that it's way bigger than just one hyperbolic plane. And so it has much higher dimension. And so as the space gets the surface, it's still just a surface. And like if you did the octagon, you would get a two-hole donut. And kind of the space of universes for playing asteroids on that, has dimension 6. It's kind of surprising. So, but there are these nice hyperbolic planes in them, but they're just sort of very special. So the donut itself is kind of the very special first case. But yes, this is there's a whole subject called algebraic geometry where you basically study these spaces of spaces. Yeah, so wonderful question. Yeah, take your time. Don't trip.
So my question is, what if all of those shapes involve sides? Let's say what if it was a circle and there are no sides or no vertices?
That's a good
Will that
question.
still work?
Well, so the issue there is what do you mean when you glue the sides? So you could do the thing where you fly into the boundary of the, so now she's saying you take a disk and it's just bounded by a circle. And now let's say, for instance, you fly into the boundary of the disk and you need somewhere to go. So let's just say you go to the opposite point. So on a circle, there's always an opposite point, like the North and South Pole, right? So you can do that, and you could code asteroids on that. And what you get is it's called a non-orientable surface called the projective plane. And it has a Mobius band in it. So if you drew the ship asymmetrically and you went up the top, right? If I have 2 points at the top, then the antipode for this one is over here, and the one for that one's over here. So if you go up the top, you'll come out and you'll be a mirror image of yourself. So that would be disconcerting in other ways, right? That's also a horror movie trope. But it's funny because it's like that's also a very small space. But that's a good question. Yeah, you can do it with other shapes like that. Another thing you can do that's closely related to all of this is called billiards. And you might think, I can go to college and study billiards and have that be my job. But if you take the polygon, instead of thinking about gluing opposite sides on a television, think about playing pool on it, where there's no pockets. It's not exciting. But the ball, when you hit the ball, it's nice in that it just goes forever. Okay? And then when it hits the wall, it has no size. It's like just a point. And then when it hits the wall of the table, it bounces off with the angles are, equal on either side. And so you can play billiards on these tables. And so you can start to ask questions like about that situation, like what's it like to play billiards on a table? And it turns out to be intimately related to the kinds of questions about playing asteroids, which is kind of strange, which I won't get into. But one, just to leave you with something beautiful you can think about, is imagine playing pool on a triangle, okay? So you might imagine that it happens that if you play pool when you're a kid and you just hammer the ball directly at a right angle into the wall, it'll just bounce back and forth forever if it had no friction, right? So that's what you call a periodic trajectory, because if you shoot it in that direction, the trajectory just repeats over and over again, okay? If you're on a square table, you could aim it at a 45-degree angle at the center of one side, and it would just bounce around in a diamond forever. Okay? So on a triangle, you could say, are there periodic trajectories at all? Okay? And it turns out that we don't know, which is kind of incredible, just for triangles. So if they're acute, then yes. And then if they're obtuse, we know it if the angles are all rational numbers times pi. And then otherwise, a professor at Brown proved that it's true, there's always a periodic trajectory, if the big angle is less than 100. He gets a slightly better number. But above that, for really flat-looking triangles, we had no idea. So that's it's something you could tell a 7-year-old, and I told my kids, and we just don't know. But anyway, that was a tangent. But
Sam, did you have another question?
no, he's sitting.
Okay. Okay, are there any last questions? Maybe one last question? Doesn't look like it. I want to let everyone know that we have a small reception going on in the Laurel Forum, and you're all welcome to come over there and say hello to Professor Kent again and join us.
Call me Autumn.
Maybe there might be some donuts left. I'm not sure.
Yeah,
So-
yeah. Well, thanks so much. Y'all have been a great audience.
Yes, thank you everyone for coming, and let's thank our speaker one more time. Thank you very much.